So the next question is, what is a language? And that's pretty simple. A language is a set of strings. For example, the string 5 star 3 is a string in the set of arithmetic expressions. The string 5 star slash is not in that set because it's not a valid arithmetic expression. And a programming language then is just a set of strings that describes a computation that can be executed by a computer. The computer can look at a string in that set and in some way interpret it as describing a computation. So the next question is, how do we take a string in that set and figure out what it means structurally, and even whether it's a member of that set? And to do that, we use a grammar. Now, a grammar is normally described in something called Backus-Naur form, or BNF, and that looks sort of like this. Here's the first attempt at a grammar that will define the language of arithmetic expressions. And in this case, we have 3 rules. The first rule defines an expression, which is a string in the language of arithmetic expressions, as being either, that's what this symbol means, a number, or an expression followed by an operator followed by an expression. And in that, a natural number is what we mean by a number. And when we say an operator, we mean either plus or minus or multiply or divide. And once we have a grammar like that, we can use it to take a string in the language and build a parse tree for that string. If we take the expression 1, we can see that 1 matches the rule. It's a natural number, so it is a num. And then a num matches the rule that it is an expression, because that was one of the options for the rule that defined what an expression was. We can also do the same thing with more complicated expressions. For example, if we take this expression 1 plus 4, we can see that 1 is a number is an expression. On the other side, 4 is a number, and a number is an expression. And in the middle, plus is an operator. And then if we have an expression followed by an operator followed by an expression, that's an expression. Now, this parse tree is sort of complicated. So if we're writing parse trees with multiple things in them, we want them to be a little bit simpler. And to do that, we can draw them like this. We don't need all the intermediate steps matching. We just need to see that the operator is plus and it has 2 arguments, 1 and 4, for the expression 1 plus 4. Now, the grammar that we had earlier for arithmetic expressions is actually good enough to tell us whether an expression or whether a string is or is not in the language or set of arithmetic expressions. For example, 1 plus 3 times 7 is a perfectly valid arithmetic expression, and we can get a parse tree out of it. As you can see, here's the parse tree for it. And the fact that we can generate a parse tree is telling us that this is a valid string in the language. And that's all good. There's one problem here. This parse tree that we generated says that first we take 1 and 3 and we add them. And then we take the result of that and we multiply it by 7. Now, if we remember arithmetic from elementary school, this isn't quite the rule that we learned for evaluating arithmetic expressions. In fact, in an arithmetic expression, you multiply before you add. The order of operations rule is that multiplication and division happen at the same time before any addition or subtraction. And so we like the parse tree that we get when we parse this expression to reflect that order of operations, so that when we go to evaluate this parse tree, we can just go ahead and do a recursive traversal of the tree and get the right answer. So in order to do that, we want to define a slightly more complicated grammar. In this case, it's only slightly more complicated. All we need to do is separate out the high precedence operators from the low precedence operators, and then separate out the combining rule, where we say a piece of the expression, an operator, another piece of the expression, into these two pieces, which we're calling expression and term. And so term includes a high precedence operator, or a number, whereas an expression includes a low precedence operator, or a term. And this does the right thing. First, you have to match any terms with the high precedence operators. Then after that, you can combine them using any low precedence operators that you match. And if we look at the parse tree that we get when we parse the same expression, 1 plus 3 times 7, using the new grammar, we can see that first it matches this term here with the multiplication operation. And then after that, it matches the addition operation. So the meaning of this is what we want, that first we multiply and then afterwards we add. Now, the thing that we want to give to the evaluation function after we parse this thing is called an abstract syntax tree. And there's not really any difference between an abstract syntax tree and a parse tree, but an abstract syntax tree is a actual data structure in the computer that the evaluation function will run on. And the key difference is that we want to label the nodes in the tree so the evaluation function will know what to do with it. Aside from that, an abstract syntax tree and a parse tree are basically the same thing. And so here's the section quiz for this first section of the lecture. Can you type in the expression corresponding to this parse tree or abstract syntax tree shown here?